Have you ever imagined someone capable of describing the motion of all the planets and even predicting the future using only mathematics? That man existed, and his name was Pierre-Simon Laplace. Known as the French Newton, Laplace transformed our understanding of the universe with ideas so revolutionary that they continue to influence science to this day. In this video, you'll discover who this genius was, how he forever changed physics, astronomy, and philosophy, and why his equations still shape the modern world. The greatest mathematicians of all time. Episode 15. Pierre-Simon Laplace.
Pierre Laplace was born on March 23, 1749, in Beaumont-en-Auge, Normandy, France, and died on March 5, 1827, in Paris. Laplace's father, Pierre Laplace, made a comfortable living in the cider trade. Laplace's mother, Marie-Anne Sauchon, came from a fairly prosperous farming family, owning land in Tourgeville. Many accounts of Laplace claim that his family were poor farmers or peasants, but these appear to be quite inaccurate, although there is little evidence of academic achievement, except for an uncle believed to have been a high school mathematics teacher. Laplace attended a Benedictine priory school in Beaumont-en-Auge as a day student between the ages of 7 and 16. His father expected him to pursue a career in the church, and indeed, the church or the army were the usual destinations for students at the priory school. At the age of 16, Laplace entered the University of Caen. Still intending to join the church, he enrolled to study theology. However, during his 2 years at the University of Caen, Laplace discovered his mathematical talents and his love for the subject. The credit for this must largely go to 2 mathematics professors at Caen, C. Gadbled and P. Lecanu, about whom little is known, except that they recognized Laplace's great mathematical potential. As soon as he learned that mathematics would be his subject, Laplace left Caen without graduating and went to Paris. He took with him a letter of introduction to d'Alembert Lecanu, his professor at Caen. Although Laplace was only 19 when he arrived in Paris, he quickly impressed d'Alembert. D'Alembert not only began mentoring Laplace's mathematical studies, but also tried to find him a position that would allow him to earn enough money to support himself in Paris. Finding a job for such a talented young man was not difficult, and Laplace was soon appointed professor of mathematics at the École Militaire.
Teaching geometry, trigonometry, elementary analysis, and statics to teenage cadets from good families, with average performance and no commitment to the subjects, provided little encouragement. But the position allowed Laplace to remain in Paris. He began producing a steady stream of notable mathematical papers, the first presented to the Académie des Sciences in Paris on March 28, 1770. This first paper, read to the Society but not published, was on maxima and minima of curves, where he improved on the methods given by Lagrange. His next paper to the Academy came soon after, and on July 18, 1770, he read a paper on difference equations. Laplace's first paper to appear in print was one on integral calculus, which he translated into Latin and published in Leipzig in the Nova Acta Eruditorum in 1771. 6 years later, Laplace republished an improved version, apologizing for the 1771 article and blaming the printer for its errors. Laplace also translated the article on maxima and minima into Latin and published it in Nova Acta Eruditorum in 1774. Also in 1771, Laplace submitted another article, Recherche sur les calculs intégrales aux différences infiniment petites et aux différences finies, Research on the integral calculus of infinitely small differences and finite differences, to the Mélange des Turins, the Turin mélanges. This article contained equations that Laplace declared to be important in mechanics and physical astronomy. The year 1771 marked Laplace's first attempt at election to the Académie des Sciences, but Vandermonde was preferred. Laplace attempted admission again in 1772, but this time Cousin was elected. Despite being only 23 years old and Cousin 33, Laplace was very angry at being passed over in favor of a mathematician who was so clearly his inferior. D'Alembert must have been disappointed too, for on January 1, 1773, he wrote to Lagrange, the director of mathematics at the Berlin Academy of Sciences, asking if it would be possible to elect Laplace to the Berlin Academy and if a position could be found for Laplace in Berlin. Before Lagrange could grant D'Alembert's request, another opportunity arose for Laplace to be admitted to the Académie de Paris. On March 31, 1773, he was elected adjunct to the Académie des Sciences in Paris. At the time of his election, he had read 13 papers for the Academy in less than 3 years.
Condorcet, who was permanent secretary of the Academy, commented on this large number of quality papers on a wide range of topics. We have already mentioned some of Laplace's early work. He not only made major contributions to difference equations and differential equations, but also examined applications to mathematical astronomy and probability theory, two major topics on which he would work throughout his life. His work in mathematical astronomy prior to his election to the Académie included work on the inclination of planetary orbits, a study of how planets were perturbed by their moons, and in a paper read to the Académie on November 27, 1771, he presented a study of the motions of the planets, which would be the first step toward his later masterpiece on the stability of the solar system. Laplace's reputation grew steadily during the 1770s. This was the period in which he established his style, reputation, philosophical position, certain mathematical techniques, and a research program in two areas, probability and celestial mechanics, in which he worked mathematically for the rest of his life. The 1780s were the period in which Laplace produced the depth of results that made him one of the most important and influential scientists the world has ever seen. This was not achieved, however, by maintaining good relations with his colleagues. Although D'Alembert was proud to have considered Laplace his protégé, he certainly began to feel that Laplace was rapidly rendering much of his work obsolete, which did nothing to improve relations. Laplace attempted to ease D'Alembert's pain by emphasizing the importance of D'Alembert's work, as he undoubtedly felt good about D'Alembert for the help and support he had given him. It appears that Laplace was not modest about his abilities and accomplishments, and he likely failed to recognize the effect his attitude had on his colleagues.
Lexell visited the Académie des Sciences in Paris in 1780-81 and reported that Laplace had widely publicized that he considered himself the best mathematician in France. The effect on his colleagues would have been only slightly softened by the fact that Laplace was right. Laplace possessed a broad knowledge of all sciences and dominated every discussion at the Academy. At the Academy, He wanted to pronounce on everything. It was while Lexell was in Paris that Laplace ventured into a new area of science, applying quantitative methods to compare living and non-living systems. Laplace and the chemist Antoine Lavoisier in 1780, with the help of an ice calorimeter they invented, showed that respiration is a form of combustion. Although Laplace soon returned to his study of mathematical astronomy, this work with Lavoisier marked the beginning of a third important area of research for Laplace: his work in physics, particularly the theory of heat, which he pursued late in his career. In 1784, Laplace was appointed an examiner in the Royal Artillery Corps, and in this role, in 1785, he examined and approved the 16-year-old Napoleon Bonaparte. This position required Laplace to write reports on the cadets he examined, but the rewards were that he became well known to government ministers and others in positions of power in France. Laplace served on many of the Académie des Sciences committees. For example, Lagrange wrote to him in 1782 that work on his Traité de mécanique analytique was nearly complete, and an Académie des Sciences committee composed of Laplace, Cousin, Legendre, and Condorcet had been established to decide on publication. Laplace served on a committee established to investigate the largest hospital in Paris and used his expertise in probability to compare mortality rates at the hospital with those of other hospitals in France and elsewhere. Laplace was promoted to a senior position at the Académie des Sciences in 1785. 2 years later, Lagrange left Berlin to join Laplace as a member of the Académie des Sciences in Paris.
Thus, the two great mathematical geniuses met in Paris, and despite their rivalry, each would benefit greatly from the other's ideas. Laplace married on May 15, 1788. His wife, Marie-Charlotte de Corty de Romanche, was 20 years younger than the 39-year-old Laplace. They had 2 children. Their son, Charles-Émile, born in 1789, pursued a military career. Laplace was appointed a member of the Académie des Sciences Committee to standardize weights and measures in May 1790. This committee worked on the metric system and advocated for a decimal base. In 1793, the Reign of Terror began, and the Académie des Sciences, along with other scientific societies, was suppressed on August 8. The Commission of Weights and Measures was the only one allowed to continue, but soon Laplace, along with Lavoisier, Borda, Coulomb, Brisson, and Delambre, were expelled from the commission, as all committee members were required to be worthy of republican virtues and hatred of kings. Before the Reign of Terror of 1793, Laplace, along with his wife and 2 children, left Paris and lived 50 kilometers southeast of Paris. He did not return to Paris until after July 1794. Although Laplace managed to avoid the fate of some of his colleagues during the Revolution, such as Lavoisier, who was guillotined in May 1794 while Laplace was away from Paris, he did experience some difficult times. He was consulted, along with Lagrange and Lalande, on the new calendar for the Revolution. Laplace knew full well that the proposed scheme didn't really work because the proposed year length didn't fit with astronomical data. However, he was wise enough not to try to overturn political dogma with scientific facts. He also conformed, perhaps more happily, to the decisions regarding the metric division of angles into 100 subdivisions. In 1795, the École Normale was founded to train teachers, and Laplace taught courses there, including one on probability, which he held in 1795.
Laplace presented his famous nebular hypothesis in 1796 at the Exposition du Système du Monde, which saw the solar system as originating from the contraction and cooling of a large, flattened, and slowly rotating cloud of incandescent gas. The exposition consisted of 5 books. The first was on the apparent motions of celestial bodies, the motion of the sea, and atmospheric refraction. The second was on the real motion of celestial bodies. The third was on force and momentum. The fourth was on the theory of universal gravitation and included an account of the motion of the sea and the shape of the earth. The final book provided a historical account of astronomy and included his famous nebular hypothesis. Laplace stated his philosophy of science at the exposition as follows: "If man confined himself to collecting facts, the sciences would be only a sterile nomenclature, and he would never have known the great laws of nature. It is by comparing phenomena with one another, seeking to understand their relationships, that he is led to discover these laws." Given modern theories about comet impacts on Earth, it is particularly interesting to see Laplace's remarkably modern take on this. The small probability of the Earth colliding with a comet can become very large over a long sequence of centuries. It is easy to imagine the effects of this impact on the Earth. The axis and the movement of rotation changed, the seas abandoned their former position, a large proportion of men and animals were drowned in this universal deluge or were destroyed by the violent tremor transmitted to the globe. Exposition of the System of the World was written as a non-mathematical introduction to Laplace's most important work, the Traité de Mécanique Céleste, the first volume of which was published 3 years later. Laplace had already discovered the invariability of planetary mean motions. In 1786, he proved that the eccentricities and inclinations of planetary orbits relative to each other always remain small, constant, and self-correcting. These and many other previous results formed the basis of his magnum opus, the Traité de Mécanique Céleste, the first 2 volumes of which were published in 1799.
The first volume of Mécanique Céleste is divided into 2 books. The first deals with general laws of equilibrium and motion of solids and fluids, while the second covers the law of universal gravitation and the motions of the centers of gravity of bodies in the solar system. The main mathematical approach here is the creation of differential equations and their solution to describe the resulting motions. The second volume deals with mechanics applied to the study of the planets. In it, Laplace included a study of the shape of the Earth, which included a discussion of data obtained from several different expeditions, and Laplace applied his theory of errors to the results. Another topic studied here by Laplace was tidal theory, but Airy, presenting his own results almost 50 years later, wrote, "It would be pointless to offer this theory in the same form in which Laplace presented it, for the part of the Mécanique Céleste that contains the theory of tides is perhaps, on the whole, more obscure than any other part. The Mécanique Céleste does not attribute many of its ideas to the work of others, but Laplace was heavily influenced by Lagrange and Legendre and used methods they developed with little reference to the originators of the ideas. Under Napoleon, Laplace was a member and then Chancellor of the Senate and received the Legion of Honor in 1805. However, Napoleon, in his memoirs written on Saint Helena, claims to have removed Laplace from the post of Minister of the Interior, which he held in 1799, after only 6 weeks. because he brought the spirit of the infinitely small into government. Laplace became a count of the empire in 1806 and was created a marquis in 1717 after the Bourbon Restoration.
The first edition of Laplace's Theory of Analytical Probabilities was published in 1812. This first edition was dedicated to Napoleon Legrand, but for obvious reasons, the dedication was removed in later editions. The work consisted of 2 books and a second edition. The first book studies generating functions and also approximations for various expressions that occur in probability theory. The second book contains Laplace's definition of probability, Bayes' rule, so named by Poincaré many years later, and observations on moral and mathematical expectation. The book continues with methods for finding probabilities of compound events when the probabilities of their simple components are known, followed by a discussion of the method of least squares, Buffon's needle problem, and inverse probability. Applications to mortality, life expectancy, and marriage duration are given. And finally, Laplace analyzes moral expectation and probability in legal matters. Later editions of The Analytical Theory of Probability also contain supplements that consider applications of probability to errors in observations, determination of the masses of Jupiter, Saturn, and Uranus, triangulation methods in surveying, and problems of geodesy, particularly the determination of the French meridian. Much of this work was completed by Laplace between 1817 and 1819 and appears in the 1820 edition of the Analytical Theory. A fourth, somewhat less impressive supplement, which returns to the initial topic of generating functions, appeared in the 1825 edition. This final supplement was presented to the Institute by Laplace, who was 76 at the time, and his son. We briefly mention Laplace's first work in physics in 1780, which fell outside the field of mechanics to which he contributed so much. By 1804, Laplace appears to have developed an approach to physics that would be highly influential for some years. This is best explained by Laplace himself. I have sought to establish that the phenomena of nature can be reduced, in the last analysis, to actions at a distance between molecule and molecule, and that the considerations of these actions must serve as the basis of the mathematical theory of these phenomena.
This approach to physics, which attempts to explain everything based on the forces acting locally between molecules, was already used by him in the 4th volume of Mecanique Celeste, published in 1805. This volume contains a study of pressure and density, astronomical refraction, barometric pressure, and the transmission of gravity based on this new philosophy of physics. It is noteworthy that it was a new approach, not because molecular theories were new, but rather because it applied to a much wider range of problems than any previous theory, and, typically Laplace, was much more mathematical than any previous theories. Laplace's desire to assume a leadership role in physics led him to become a founding member of the Société d'Arcueil around 1805. Together with the chemist Berthollet, he founded the society, which operated from their homes in Arcueil, south of Paris. Among the mathematicians who were members of this active group of scientists were Biot and Poisson. The group strongly advocated a mathematical approach to science, with Laplace playing a leading role. This marks the height of Laplace's influence, which also dominated the Institute and had a strong influence on the École Polytechnique and the courses students studied there. After the publication of the 4th volume of Mecanique Celeste, Laplace continued to apply his physics ideas to other problems, such as capillary action, 1806-07, double refraction, 1809, the speed of sound, 1816, the theory of heat, particularly the shape and rotation of the cooling Earth, 1817-1820, and elastic fluids, 1821. However, during this period, his dominant position in French science came to an end, and others with different physical theories began to grow in importance. The Société d'Arcueil, after a few years of high activity, began to become less active, with meetings becoming less regular around 1812. Meetings ceased completely the following year.
Arago, who had been a faithful member of the Society, began to favor the wave theory of light as proposed by Fresnel around 1815, which was directly opposed to the corpuscular theory that Laplace supported and developed. Many of Laplace's other physical theories were attacked. For example, his caloric theory of heat was at odds with the work of Petit and Fourier. However, Laplace did not admit that his physical theories were wrong and maintained his belief in fluids of heat and light, writing articles on these topics when he was over 70 years old. At a time when his influence was waning, a personal tragedy struck Laplace. His only daughter, Sophie Suzanne, had married the Marquis de Portes and died in childbirth in 1813. The child, however, survived, and it is through her that Laplace's descendants exist. Laplace's son, Charles Émile, lived to be 85 but had no children. Laplace constantly shifted his opinions with the changing political events of the time, modifying his views to adapt to the frequent political shifts typical of the period. This manner of conduct contributed to his success in the 1790s and 1800s, but it certainly did not contribute to his personal relationships with colleagues, who viewed his shifts of opinion as mere attempts to curry favor. In 1814, Laplace supported the restoration of the Bourbon monarchy and voted against Napoleon in the Senate. The 100 Days were an embarrassment for him the following year, and he conveniently left Paris during this critical period. After that, he remained a defender of the Bourbon monarchy and became unpopular in political circles. When he refused to sign the French Academy of Sciences document supporting freedom of the press in 1826, he lost his remaining friends in politics. On Monday morning, March 5, 1827, Laplace passed away. Few events would have caused the Academy to cancel a meeting, but they did so that day as a mark of respect for one of the greatest scientists of all time. Surprisingly, there was no quick decision to fill the vacancy left by his death, and the French Academy of Sciences' decision in October 1827 not to fill the vacancy for another 6 months did not result in an appointment at that time, and it took several more months for Poussin to be elected as Laplace's successor.
Pierre-Simon Laplace showed us that the universe can be understood through reason, and that, with mathematics and curiosity, we can see far beyond what meets the eye. Laplace's legacy is a powerful reminder that the pursuit of knowledge never ends. Now, I want to hear from you. Do you think Laplace was as brilliant as Newton? Leave your opinion in the comments. And if you enjoyed this journey through the history of science, leave a like, subscribe to the channel, and share this video with those who love science and curiosity. Until the next video, and keep exploring the universe of knowledge.